Hello, this is Jack Jackson. In this video and in this section, we're going to be doing a paired data t-test, before and after type data. This corresponds to problem 35 in my homework set 4, as it is as of the recording of this video. Now recall that we have two dependent samples like paired data. We have paired differences before and after measurements. This is one of the most common and useful situations. It's not really two samples, it's one sample of ordered pairs. So what we do is we compute the differences, after minus before, and we look for a positive increase or negative decrease, and we treat the differences as one sample. Okay, so use a one sample z-test if the population standard deviation is known, rarely, and a one sample t-test if the population standard deviation is unknown. Working with paired data sets is one of the most common and powerful uses of inferential statistics. One example of this is looking at before and after measurements. This is particularly useful because if the before and after measurements are for the same subjects, then it eliminates many confounding variables. When we have paired data, we really don't have two samples. Instead, what we have is one sample of ordered pairs. Just as in the paired data t-interval, what we do is compute the set of differences, after minus before, to get a one sample of changes. Positive difference means there is an increase in the measurement, and a negative means there is a decrease in that measurement. Now, we just treat these differences as one sample, use a one sample z-test if the population standard deviation is known, and a one sample t if the standard deviation is unknown. Here's an example. In USA Today, September 17, 2009, a Bloomberg News poll was quoted to find that Americans were planning on keeping spending down. Suppose a group of 15 households noted their household spending in March and then notated their household spending 6 months later in September. The mean of the paired differences in spending was calculated to be negative $75.50 with a standard deviation of $66.20. Does this sample give sufficient evidence of decreased spending at the alpha equals 0.05 level? What is the 95% confidence interval for the change in monthly spending? Notice that I'm asking you for both a hypothesis test and a confidence interval. Putting those two together is a very powerful way to do statistics, and it's highly suggested. The good news is, of course, we can do both these at once. In fact, I think you actually know enough, and you should probably at this point could do this on your own. So I'm going to ask you to stop the video, do this on your own and then on your calculator, use your built-in apps, and then come back and check your answer. Press pause now. Well, let's first see what we've got. We're testing means with population standard deviation unknown, so that's a one sample t-test. And a little bit later we'll be doing the confidence interval for the means, mean change, which is a one sample t interval. The null hypothesis is that there is no change, so the mean change would be 0. Notice if you're looking at this, that's a typical scenario. So if there's no difference in spending before and after the average should be 0. So that's going to be our null hypothesis. The alternative hypothesis is that the spending went down, so that's the change, mean change is less than 0. Now we ran this through the calculator here by pressing stat, test, and go to t-test, hit statistics. The mu naught is 0, the x bar is negative 75.5, the s is 66.2, n is 15, the left-tailed test, calculate, and we get that. See the e negative 4, so it's 0.30 and then a 29. So that's a very, very small p-value, very strong evidence to conclude that Americans average less on household spending in September than in March. So how much less? So anytime, especially when you reject the null hypothesis, you should also include a confidence interval. So how much less? Well, let's convert to 95% confidence interval for the mean change in spending. So then we run another program, another test, actually an interval this time. So you do stat, go to test, and this time choose t-interval. Again, statistics. If you've run it right after this one, actually numbers are probably already in there, but change them if you need to. 95% confidence level. This says calculate under this black bar. Click on that, hit enter. It reminds you of your data you put in for your x bar, your statistics you put in for x bar, s, and n. But then it also returns that confidence interval of negative 112.2 to negative 38.84. So we are 95% confidence the mean change in spending was a drop in spending of somewhere between, let's say $112 and $39. Let's give you guys another chance to work one of these. 10 subjects with borderline high cholesterol levels were randomly recruited for a study that involved taking a nutrition education class. Cholesterol readings were taken before they started and then 3 months after the class. The following table gives the results. Subject 1, pre-test 295, post-test 265, and so forth. Is there sufficient evidence to support the conclusion that the class helped lower cholesterol levels? Use the alpha level of 0.05 and the corresponding confidence level of 95%. Make a confidence interval for the mean. So do a hypothesis test and a confidence interval. Do this one on your own. Come back when you got it worked out. Press pause now. Well, here's worked out. Put your data in L1 for pretest in the same order, post-test there. Put your cursor on L3, push L2 minus L1 so that we get a positive difference. Means it increased. A negative difference means we decreased. Go to a t-test, say it's in data, give a mu naught of 0, a null hypothesis is there's no change in cholesterol. Give them the list of differences, which is L3. Frequency 1, we think that if it did well, then that was a negative change. So we want to, did it lower cholesterol? So that's a left-tailed test. So that's the less than here. Calculate that. You get the third screen here. The main thing we want to pull out of that is the p-value, 0.00397. Okay. Which is less than 0.05. 0.004 is less than 0.050. So there is enough evidence to reject the null hypothesis, especially when you do that, but maybe anyway, you're going to want to do a t-interval as well. So now to go to the t-interval, do, let's see, we have our data somewhere, so we're going to select data rather than statistics, so it's blacked out here, but that's data. And our data is in list 3, frequency 1, confidence level is 0.95. Calculate, it gives us this confidence interval. So let's write down our conclusions. A one-sample left-tailed t-test was performed on the set of differences. This test produced a p-value of 0.00397, so at the alpha equals 0.05 level, there is sufficient evidence to support the conclusion that the mean cholesterol levels were lower after 3 months of this class. A 95% confidence interval for the mean change in cholesterol level is negative 43.83 to negative 8.774. So we know that there's a 95% chance that on average their cholesterol is going to be lowered by about 8.8 points, all the way up to lowering that by about 43.8 points. So once again, notice in this conclusion we had enough evidence to reject the null hypothesis, so we determined the amount of change in cholesterol level is significant. When this is the case, it is a really good practice to give a confidence interval for the amount of change using the same alpha level. In this example, not only do we see that the class was effective in lowering the cholesterol, but that the average amount of cholesterol change was a lowering of cholesterol between 8 and 44 points. Combining a hypothesis test with a confidence interval yields more information. So you should now be able to do all kinds of one-sample t-tests and t-intervals, including problem 35 on homework set 4.